Hey guys, welcome again. Hope you had a nice break. Today we'll be going through decision trees, which are pretty important and pretty widely used in machine learning and data science. So let's just get straight into it. First of all, what is a decision tree? These are things that you'll be familiar with, and they're very easy to understand. You essentially just follow kind of a sequence. It's like, is this variable, for example, is this variable green? If yes, go down one branch, if not, go down another branch. And then you just kind of keep going down like that until you get to the end. So this is a decision tree for some fruits, and you can just follow along and see if something's not green, it's not red, and it's not round, then this decision tree predicts that it's a banana. So today what we're going to learn about is how to construct these kind of decision trees and how to do it automatically. So the algorithm for the decision tree is pretty simple. You consider all the potential variables that you can kind of split on. So for the fruit example, maybe you can split on a fruit's size or its shape or its color or something. You pick the best one for it to split on, and then you split on it, and then you just repeat the process for each kind of individual node. I might be referring to a bit of like notation. So it's a decision tree, so a lot of the terminology is tree related. Often just the start is called the root, and then each split can be called a branch, and then at each split point it's often called a node or a leaf. So if I kind of refer to those terms, that's what they mean. So yeah, as I said, the algorithm, the first stage of it is to decide which variable to split on. And how can you determine what's the best variable to split on? So heuristically, the best variables to split on is one that separates the data into its classes quite well. So for example, here, if I split on some variable and I get mostly circles in one node and then mostly stars in another node, that can be considered a pretty good split. If it perfectly splits the blues and the stars, then that's kind of a perfect decision tree and we don't need to go any further. If it splits it and it's kind of still half-half either way, then that is not as good of a split. So how can we measure this idea of how well the data is separated? Well, we're going to be using a measure that's called entropy. And entropy, you might have heard it from, say, physics or something. It's essentially how messed up everything is. So kind of our universe is always going to a state of entropy because the particles and stuff, if they start out uniform, then they eventually disperse and get all mixed between each other. And ideally what we want is we want low entropy because that means things are nice and ordered. So if in the previous examples all the circles are in one node and all the stars are in another node, then it's very ordered, which means there's low entropy. So the formula for entropy is given by negative of the sum of pi times log 2 pi for all I. So what pi is the proportion of things in each category. And we have log base 2 here. So if we take if there are only two categories, like there was in the previous example, just circles and stars, then the formula is just the proportion of one category times the log of that proportion minus 1 minus the proportion. And the graph of that looks like this. So you see, if the proportion is 50%, and that means it's about as mixed up as it can be, then the entropy is at its highest point. Whereas if the proportion is 0 or 1, which are essentially equivalent, then the entropy is 0, as low as it can be. So how can we use this measure of entropy to decide which variable to split on? And we construct a new measure called the information gain. So what this is S is our sample data set. It's got a mix of all different categories, and A is some variable on which we can split on. So for example, in the fruit one, it could be the shape or the size or the color. So what this is trying to measure is how well we reduce the entropy, or in other words, how much information do we gain from splitting on this variable A. And that's just equal to the original entropy of S. And then over here what we have is we've split on all the values of A. So if A was maybe color, we have the entropy for each color. So entropy for all the green fruits, or the red fruits, or the yellow fruits, etc. And then this is the number of samples in that category. And this should be absolute value of S because it's the number of samples in our original one. But essentially you can think of this as a weighted average of the resulting entropy. So the easiest way to do this is through an example. So I have an example here. You might not be able to see it, but it's alright, I'll write it on the board. So we have our S containing 29 positives and 35 negatives. And then on the left we split it using variable A1. And then on the right we split it using variable A2. So if we split it by variable A1, we get two nodes, one with 21 positives and 5 negatives, another with 8 positives and 30 negatives. And if we split by A2, we get one node with 18 positives and 33 negatives, and another node with 11 positives and 2 negatives. So let's work out the information gain from splitting on A1 first. So we have gain by splitting S on A1 equals, well, first thing we want to find out is the original entropy of S. So entropy of S and sometimes that's denoted by the letter H. So that's negative. And what's the proportion of one category? It's 29 on 64. Log 2 29 on 64 minus the other proportion, and I'm gonna just put that in my calculator. 64. Feel free to verify this in case you get it wrong. So I get 0.9937. So this will equal 0.9937 minus. So now we have to consider all the possible values on which the split produced. In this case there's 2. And it's a weighted average, so we care about how many samples are in each node. So the sample in the left node, there's 26 of them out of the 64 original ones. And then from there we calculate the entropy of S. Seems like it's true. So S A1 true plus And in the other one we have 38 samples. And we calculate the entropy of S, A1 false. And now again we have to calculate the entropy for this node now. So that's going to be minus 21 on 26 log 2, 21 on 26, minus 5 on 26 log 2, 5 on 26. So that's this part. And then we calculate this one, and now find the entropy for here. That's 8 on 38 log 2, 8 on 38. It's negative minus 30 on 38. That's a lot of calculations. Okay. 0.9937. So 0.9937 minus 0.2946. Then that equals 9937 minus 2582. So that's the information gain after splitting on A1. So we can think of that as how much the entropy decreased if we split on A1. Now that took a while, so I'm not going to do it for A2, but what do you guys reckon the information gain on A2 would be? Would it be bigger than or smaller than this, if you were to guess? So here it's 21.5, 830, here's 1833 and 11.2. So what are your guys' intuition kind of say?
A1?
A1 would be higher? Lower? Why do you think higher?
Because like split is better after the split we get on A1. Like
Why do you say that?
like let's say here like we have more negatives on that side and more positives on that side. So that is split.
Sure. Yeah, I think I agree. Okay. So if you split on A1, you see like 21.5 is like more than 4 times the negatives here, and then 30 8, there's more than 3 times one of 3 times negatives and positives, so it does pretty well. Whereas over here we get on the left note 18 and 33, and that's not even twice as much as the positives. So A2 didn't split this one very well. It split this one alright, but it didn't split this one very well. So I suspect if we do the same calculations, the information gain will end up higher on here. So the idea with decision trees is that for every possible variable you could split on, you calculate the information gain. And then you find which one has the highest information gain, and you pick that one to split. So since this one has a lower one, we kind of disregard it, and we just go with this. And then this is what our tree will now look like, and you do the same process, but now on this node and this node. So are there any questions on how that works? Okay, cool. So when does this process kind of stop? There's a few ways that we can make it stop. First thing I'll talk about is if you just grow up to completion. So that's where you just keep letting it grow until there's no possible way for it to grow further. And that could be because, well, if all the nodes are already kind of pure, like they all contain the same category, then there's no reason we need to keep going. In fact, we can't. So that's one way it can stop. And the second way is when there's no more variables to split on. So even if the categories aren't purely one thing, if there's just no more things that we can split on. So if we take two very similar fruits, for example, let's say mandarins and oranges, and let's say we have data on their shape and color. They're both round and orange, and even though they belong in that node, there's nothing else, no more information we have to split, so we physically can't grow the tree out anymore, and we say the tree's growing to completion. But when we grow a tree to completion, it's prone to overfitting, because if we have a lot of variables, we might be able to just have like a lot of different nodes and branches, each with its own like single observation in it. So we're getting kind of very specific with what we're looking for. And that's just a classic example of overfitting. So an important thing we have to take into account is how to prevent overfitting. And often this is called pruning, again going with the tree metaphor. And the two types are pre-pruning and post-pruning. So with pre-pruning, we stop growing the tree before it reaches completion. And with post-pruning, we let it grow to completion and then cut it after it's been completed. And we'll have a bit of a look at each of those. So with pre-pruning, there can be several different criteria. So one could be based on a statistical significance test. So we haven't covered hypothesis tests in these workshops, but essentially, let's say I have kind of this room of people, and let's say I have information on your I don't know, degrees or something, and then I try and split you guys on your age. Now the proportions will probably be different, just because I split a bunch of you guys up and like you'll end up with different proportions. But will it be statistically significant? So let's say I get all the like 22-year-olds and over, and all the 21-year-olds and over under, and let's say, for sake of argument, like 50% of the 21 and unders are computer science students, and 60% of the 22 and over are computer science students. Now, does that mean that the people in the 22 and over category are more likely to be computer science students? Or just by these two numbers, 60%, 50%, yes, but we're not taking into account, you know, the random noise, like the randomness of you guys as a group of people. So if the difference was say like 50% and 51%, you probably have more reservations about saying that there's a significant difference. If it's like 10% and 90%, you can probably more confidently say there is a difference. And the way to, I guess, formally recognize when there is a difference that you're comfortable acknowledging, you do that with a hypothesis test. But we won't go through that today. It's just something that is very prominent in statistics. And one example of that is the chi-square test, and we're essentially testing if there's enough of a difference between the proportions to say that, okay, there's probably some causation going on here, or at least some correlation. So when you decide to try and split on a certain variable, you might try and run this statistical hypothesis test to see if there is any significant difference on splitting this variable. So that's one way of doing it. Another way of doing it, which is kind of related, is to not split when the number of samples in a node is too small. So that could be, that's kind of just any arbitrary number you'd like to pick. So maybe if each node has 5 observations, then at that point you decide, okay, it's too small. If I split it, then it's not going to be significant, so I don't want to touch this node. It's going to stay at 5 samples. And another way of pre-pruning is to stop growing after a specific number of splits. So after maybe 1 split and then 2, 3 splits, you might say, okay, I only want my tree to have a maximum of 3 splits, or 5 splits, or whatever you want. That's another way of specifying when to stop growing the tree. Now, one potential problem with pre-pruning is that it could stop growing the tree prematurely. So it could decide by any of these measures that it's not worth splitting the tree again. But in reality, if we split it again and again, that turned out to be a better tree than if we just stopped prematurely. So one example of that is the XOR case. Now, you can think of a split as taking one of these variables and splitting it like that, and then another split being taking this variable and splitting it like that. So you can see here, these classifications can be perfectly classified because we can split it down to x, and then for this side of the x we can split the y here, and then this side of the x we can split the y here, and everything's perfectly classified, which is great. But consider if we apply pre-pruning to this tree. So let's say we're given this, which looks pretty much 50-50. There's a few more of these green ones, but let's say, for sake of simplicity, it's about 50-50. And then we split it down the x-axis. Now what we get is, we get something that's pretty much 50-50 again. So by our pre-pruning ideas, it's not a very useful split. And similarly, if you split it down the y-axis, again, it will still be 50-50. So if we don't let this tree go out to completion, it might decide to stop. It might just decide there's no way to split this tree, because any way you try and split it first, nothing will come of it. So yeah, in this instance, pre-pruning will actually stop the tree from becoming anything useful. So post-pruning, as I mentioned, is letting the tree grow out to as big as it can, as big as it wants to, and then from there trying to decide which branches to cut off, which ones aren't important. And I'm just going to talk about the reduced error pruning method, and this relies on cross-validation, or not even cross-validation, just validation in general. So if you remember, with our data set, we would usually split it into the test data set to build our model on, and then our validation data set to test our model on, or train data set, test data set. Kind of interchangeable names to an extent. So the idea is, when we test our model on the test data set, that's kind of a good indication of the actual effectiveness of the tree. So if the training error doesn't matter too much, as long as the test error is small, then that's what we want. So we would split our data into training and test, and then from our complete tree, we would use that to try and predict on our test data set, and then we'd say, okay, what if with this tree I just got rid of one of the branches? Now, how does that do on the validation set, on the test data set? Did it improve the test error? And if it did, by how much? And then you would record that, or the computer would record that. And then you try and prune another branch and another branch, and for each of the branches you record how much did it improve the validation error. And the idea is the validation error will be improved when you remove one of the branches, because that's kind of removing one of the branches that's overfitting. So usually with this kind of method, it's a greedy approach, which means you just select the branch that reduces the test error by the most and cut that off. And then you just repeat that process with the remaining tree until cutting more branches won't reduce the test error. And at that point, we can kind of say, okay, this tree is doesn't overfit and performs well on unsynced data. So far, we've only talked about categorical variable splits. So things like, what's the color of a fruit? It can be red, green, yellow. These are all categories. But what if we have a numerical variable? So something like the diameter of the fruit or the weight of the fruit. How can we split using numerical values? So the way to do it is to kind of create kind of two categories using a greater than or less than approach. So say we have the weight. Where's the eraser? Thank you. So say for the weight of the fruit, I have, I don't know, maybe like 50, 100, 120, 150, 250, etc. So what I would do is I would pick kind of the midpoint between two consecutive numbers and say the first split would be like less than 75, greater than equal to 75. And I would test on that. And then, so that's kind of like one split. I would find the information gained for that, record it. And then for the next split, I just go between these, so less than 1 to 10, greater than equal to 110, and split on that. And just do that over and over. So yeah, you could end up with something that looks like this. So here we're trying to classify between the red data points and the black data points. And this is the decision tree that represents what's going on there. So is x less than 0.27? If it is x2 less than 0.32, etc. Yes. Thank you. And last thing I'll talk about with just trees is regression trees. And again, that's just considering what if we want what if we want continuous responses instead of categorical responses. So before, say with the fruit examples, again, we have a categorical response variable, apple, banana. But what if we want some numerical stuff? So essentially what you kind of do is at each node, you probably just take the mean of whatever's there. So here is an example that's trying to predict miles per gallon using the MT cars data set. And you can see at the end of each node, we just have some number saying, okay, I predict that if horsepower is greater than 139.5, then miles per gallon, I'm just going to predict that as 19.64. And so if you have a continuous variable and continuous response, continuous x and y, you get something that looks like this. So each split, like you can split on multiple times, so maybe it starts here, and so it says, is it less than -1? And then there's another split, so if it's less than -1, is it less than -2? And from there there's another split that says, is it less than -2.5 or something. And at each kind of bucket we just have a single number representing our entire prediction for that bucket, which is why we get this kind of jagged shape. So with a regression tree, how do we calculate, I guess, the information gain? Because we can't use the entropy anymore. That relied on having proportions of different categories. But here we have numerical variables, so there's no kind of categories, there's no proportions of that. So instead what we do is we try and minimize the variance. So the idea is very similar, and the formula is pretty similar as well. So the variance of the data after we split on variable A, well, that's just going to equal the weighted sum or the weighted average of the variance of each subcategory for each category of A. And it doesn't really matter if it's like n or n divided by capital N, because we just want to minimize it, and a constant is not going to affect the order of the variance reduction. So now that we know about decision trees, just going to talk briefly about some properties. So the first one that's very well liked is that it's easily interpretable. And that's, I guess, the opposite of something like a neural network, where it's almost impossible to interpret what's going on. But with a decision tree, you can see exactly at each stage, and you can understand exactly how the algorithm is giving you an answer. And from that, you can try and understand some more like natural relationships between the variable and the response. So, for example, in the fruit one, maybe you notice that all the big fruits tend to be a certain color or something like that. It's easy to be able to find these kind of relationships with decision trees. And it mirrors human decision making. It's probably the algorithm that mirrors human decision making the most, because every time we make a decision, it's probably, if you think about it, just a bunch of if-else statements that leads us to make our final decision. And that's what decision trees are. It easily accounts for interactions. So after you split on one variable, it tries to split on another variable. So it takes into account how the color of a fruit interacts with the shape of a fruit. Whereas with something like linear regression, the most basic form, everything is kind of assumed to be independent of each other. So y equals something times x1 plus something times x2. If you want to model some kind of interaction between x1 and x2, you'd have to add in an additional term, y equals x1 plus x2 plus something times x1 times x2. Or maybe if that's not an interaction that works, maybe you have to be even more fiddly and say x1 times x2 squared or something. So decision trees make it really easy and really automatic to model the interaction between different variables. And it's greedy. Now what do I mean by greedy? Now notice that when we were calculating the information gain, we just straight up pick the variable that has the highest information gain at that point in time. Now because of that, it's greedy, but that doesn't necessarily mean it will end up as the best decision tree. Because maybe it'd be worth splitting on a different variable that doesn't give you as high an information gain. But if you split further using that design of the tree, you'll end up with something that's kind of better. But that's something that's kind of very hard to account for, so decision trees are generally all greedy, and it generally seems to work pretty well in real life anyways. And I can't remember if I've talked to you about the variance bias trade-off, but with a decision tree you have a high variance and a low bias, which means like if you change the data just a little bit, that could change the first node, the first split of the decision tree, and that will kind of change all subsequent splits. So kind of what small changes in the data will lead to massive changes in what the tree looks like. And that's kind of the definition of a high variance. But that being said, because of these kind of like desirable properties, it takes into account interactions and all that kind of good stuff, it does have a low bias. So what we're going to talk about now is variations on the decision tree. And these are generally trying to reduce the variance while keeping the bias low. So the first one I'm going to talk about is called random forests. Again, sticking with the tree metaphor. Now, with random forests, the final model is made up with a lot of decision trees, and that's why it's called a forest, because it's made up of lots of trees. And the final decision, what it outputs, is a vote between all the trees. So maybe if we're trying to classify fruit, we build like 100 decision trees, and all of them are slightly different. And then at the end, our model will just say, okay, well 70% of the trees voted orange, 20 voted mandarin, and 10 voted banana. So we're just going to go with the majority vote and say that it's an orange. And that's how a random forest works. Now, what's the properties of each tree inside a random forest? Generally, the decision tree is smaller. So it's not going to be grown to completion. It's going to be kind of a smallish tree to reduce the variance. And each decision tree is built with random features, which means, so with the fruit we have information on, say, the size, the color, the weight, the shape. We just pick a random number. So for tree number 1, maybe I build a tree but only use the size and the color. Then for the second decision tree, I only use the weight and the shape. And for the third one, maybe I'll use size, color, and shape. And for the fourth one, I'll use some other random configuration of features. And in addition to that, we're also going to be using a random sample of data. So instead of building our decision tree on the entire data set, I'll just pick a sample, pick some random features, and build a decision tree there. And then for another decision tree, I again pick a random sample to train on, pick a random number of features to use in the model, and build the decision tree there. So that's why it's called a random forest, because we're introducing this kind of randomness within each tree. And the idea is, we keep them small, we use random things to avoid overfitting. We don't want to use too many features on the entire data set, because then we're just modeling that specific data set. But if we randomize what each data set is and what the features are, we can try and remove as much of the bias within the data set as we can. So, yeah, the process of using random sampling, that's often called bagging, which is short for bootstrap aggregating. And the process of using multiple different models and then combining them all together to produce a final output, that process is called ensembling, because it's kind of an ensemble of models that lead to our final decision.
One question.
Yeah.
In bagging, do we replace, just take some samples by replacement, or just unique samples but random ones?
I believe, I think it's up to you, but I don't think it matters too much. I think
one thing called boosting as well. I think they differ in that way. Bagging and boosting.
Boosting is actually what I'm going to talk about next. It's not sampling with or without replacement. I don't think is an important thing in boosting. Daniel, do you know?
Well, I think because it's bootstrapping, didn't they just you can do it with replacement? I think.
Yeah, I think from what
Might be
I've
really
read,
easy.
it's always been with replacement.
Yeah.
But I can't think of a reason why without replacement would also work.
Yeah, it shouldn't.
Yeah.
It's expanded.
Yeah. So I think the answer is generally it's done with replacement.
But just trial and error. Just check.
Cool. Any other questions on random forests? Cool. What's next? So this is kind of a visual representation of what a random forest might look like. Although, not really, because these models aren't random forests, but this is more an example of bagging, I believe. So I'm not sure if you can see, but there's some grey lines here, and each of them is an individual model that's used a certain number of these data points, but not all of them, which is why they're kind of slightly different. And then the final model is just the average of all our different models. So that's an example of bagging and ensemble. So the next thing I'm going to talk about is a GVM, a gradient boosting machine. And the idea of that is similar in the sense that we again have multiple decision trees. But this time, instead of looking at having a vote, what happens is you build a small tree, and then you look at the residuals. And then you build a tree on those residuals, and then look at the residuals again, and just keep building trees on the residuals. So this is an example of one, like 3 iterations of boosting, GVMs. So this is the first tree that's been built, and then the data points here are the residuals from here. So that's the actual minus the predicted. So you can see like these 2 data points are higher and these 2 are low, so they correspond to these ones here. And then you build another decision tree on these residuals and look at the residuals from here. And then you build another decision tree on those residuals and kind of keep going. Yep.
So like between tree 2 and tree 1, so like we subtract residuals from the original value or from the previous value of tree, like from tree 1.
From this one. So these the residuals.
Like for tree 1, I'll subtract from the predictive value from the ground truth, right? For tree.
No, from tree 2.
No, for tree 1.
Oh, for tree 1. Yeah, sorry, yeah.
So for tree 2, I'll get the value tree 1 ground truth minus tree 1, and then for tree 3, I will get value for tree 2 minus tree 1 or tree 2 minus ground truth. So that subtraction part is always ground truth or the previous tree.
The previous tree. So the residuals of the previous tree. And yeah, so the idea is the first decision tree won't do that well, but the next one will improve it slightly. The next one will improve that slightly. And the end model is just the sum of all these decision trees. And quite often, these trees are so small, it's just one split, and yeah, that's called a stump. And the idea is you build, like thousands of these small stumps and add them together, and that's one way of reducing variance and maintaining a low bias. And GVMs are actually, I don't know, do you have any comments on GVMs? They're quite
Very good.
popular. They're very good.
Yeah.
Yeah.
Very good.
Cool. Next slide. So, if you think about it, if we're always modeling the residuals, eventually we can just model the data exactly. Because whatever residuals we're left with, we can just add another model onto that. So if we add enough of these decision trees, then we will eventually replicate the entire data set, and we get into, we overfit, essentially. So how do we prevent overfitting? Well, we come back to the whole idea of test and validation sets. Now, if you remember in week 2 or something, I talked about how the more complex the model is, the more it can fit, the more complex the shape is, and the more prone it is to overfitting. Now, what complexity is in a GVM model is simply the number of trees. And this is kind of a sequential process. So we add more trees, and then we look at what happens to the training and the test set. So the training set will always kind of go down because we're always fitting to the residuals. We're always improving on our residuals. But then we get to a certain point where the validation error or the test error will start going back up again. And that's when we can say it's overfitting. Because although it's doing better and better on the data we model, it's starting to do worse on the unseen data. So there are some really good properties of GVMs. So one of them is that you can kind of get marginal influence graphs on each of the variables. So here we're trying to predict whether a flower is of the Virginia species, and then we see how we have different attributes on each flower. So it's sepal length, sepal width, petal width, and we can see how as the sepal length increases, the probability that it's Virginia increases, and then we can see all sorts of kind of different and interesting relationships between the variable and the response variable. And if you go to the next one, another thing that GVMs are good at is telling you which variable is important. So the way it does that, remember, these are all made from decision trees. And trees split things and record the information gain. So if you have variable A that gives you a huge information gain, and variable B that gives you a slight information gain, then you might be able to say that variable A is more important in determining what the end predicted value is. So if we have hundreds and thousands of these kind of trees, then we can look at which variable was split on each tree and how much information gain was of a result of splitting on each variable. And from there we can calculate how important each variable is to predicting our target variable. And this is useful because it's, at the end of the day, it's an algorithm, and humans have much more knowledge than an algorithm. So if you see a couple of variables in here and you think, oh, they're probably not related to the target variable, they're probably just spurious correlations, I want to remove these from the model, then you can very easily do that. And at the same time, you can very easily see, oh, okay, this variable is very important if we're trying to predict fruit or predict whatever. Let's say we're trying to predict the credit score of someone, whether they're going to default on their loan, and you can see, okay, their income seems to be a very high importance. Cool. So that's all I had. I was going to go through a bit of R code to just show you how things are in GVMs. And I might just quickly run through that, and it's very simple. As you can see, it's not showing on the screen. I don't know. Okay. Anyways, so here I've imported the GVM library. Deploy, I don't think I actually used deploy, but that's right. And then the dataset I'm using is called Iris, and that's one of the many inbuilt datasets already in R, and it gives you information on the sepal length, sepal width, petal length, and petal width, and the species of different flowers. I think there's there's 150 observations, each with its with these 5 variables. And then the next command I do is just a very simple GVM call. So I'm trying to fit a GVM to this, And I'm trying to predict the sepal length using the sepal width, petal length, and the species of the flower. And I specify a few hyperparameters. So, actually, let's get rid of this one. So I run it, it will train, and then what this does, I ask it to find, okay, how many trees do I want to stop at? And again, this is talking about looking at the training error and the validation error and seeing when it kind of stops. So when it starts increasing again. So R automatically does that for you. A summary will show you which variables are the most important. It's not showing up well there, but the next ones you can plot what I was talking about before, the marginal effect. So how sepal width affects what am I trying to predict? The sepal length.
Species.
Yeah. So how sepal width affects sepal length, how petal length affects sepal length, and everything like that. And you'll notice it's just kind of like a positive trend. The bigger the width is, the bigger the length is, and that kind of makes sense. And another thing you can do in R is, say for this marginal effect graph, you see it generally goes up and then it dips down slightly. Now that's probably not something we'd expect. That's probably a result of some noise in our data. We'd probably expect this to always increasing. And we can actually specify that option in the GBM function. We can say, okay, I want, so in this case, variable 1, 2, and 3 to all be monotonically increasing. And you can see it kind of like maybe decreases there as well, which isn't something we want. So again, I'll just run the model, but now with this new specification saying that, okay, as sepal width increases, I don't want to predict that sepal length decreases. And then I do everything again. And now you see the marginal effects don't decrease anymore, which is something that makes sense. Anyways, so yeah, that's it for today. Hope you guys found that useful. And then Daniel will go over natural language processing in a bit. Have a bit of a breakdown. Thanks for coming.